This is our review for chapters 1 through 3, describing data and relationships. So chapter 1 talked about exploring data. This whole section, by the way, describing data and relationships, makes up approximately 20 to 25% of the AP exam. You'll be guaranteed at least one of the FRQs, if not a couple, talking about different ways of describing data. Individuals, the objects described as a set of data, could be people, places, or things. Variable, we have two different types. Categorical are definitely for proportions. We've been dealing with that in inference. And then there's also quantitative, in which case you'll have an average. The distribution of a variable tells us what values a variable can take and how often it takes these values. We've been learning with inference, actually back in the first chapter, that you can do a lot more with quantitative variables. Quantitative variables, usually you get to describe your distribution, and you'll be asked to do so a lot more frequently than you would with categorical variables. And of course, that was usually with SOCs. And we'll mention some other things based on the type of graph that you use. With categorical variables, we usually used a two-way table to describe things. And then there's marginal and conditional distributions with it that we'll also talk about on the next page. So categorical, for your pie chart, first off. Basically, it's just your circle, and it breaks down, there's only one variable, and it breaks down your data into percentages. And of course, the whole circle has to add up to 1 or 100%. You could have, oh, that's a peace sign. Huh. Let's make it more. You could have a whole bunch of different categories going on, and the whole thing would add up to 100%. Now we have our bar graph or bar chart. This is just on one variable still. You're taking that one variable and breaking up by its characteristic. You have your frequency on your y-axis, and you could have like a cat, a dog, fish, whatever you want. And then of course they would have different amounts. And that's represented with how high the bars are. Side-by-side bar graph basically takes into place two variables that you're comparing. You're still having your frequency on your y-axis, but now one variable is on the bottom, so you could have your cat, dog, and fish still. Only you're going to have different representations on your graph. So we could say that purple equals girls, and blue, or whatever color this is, equals boys. So now your second variable is within the bars. So for cats, let's say this many girls have cats, and this many girls have dogs. And fish, whereas the boys, maybe there's that many that have cats, there's this many that have dogs, and this many that have fish. And then all the blue bars would need to add up to the total, or 100%, and all the purple bars would need to do the same. Segmented bar graph. It's pretty much a combination of a pie graph and a bar chart. And once in a great while you might be asked to create a segmented bar graph. So if you're not used to making one, it might take a little more thought and throw you if it's on the AP exam. You still have your frequency on your y-axis, usually represented again as proportions or percentages. But within each bar is going to add up to 1 or 100%. But with these bars, we're going to separate cat, dog, and fish, but on the inside we still have our boys and girls. So the boys, as far as the cat, maybe they're less than the girls, a little bit. For dogs, they're a little bit more. And then for fish, they were a little bit more as well. I'm not sure proportion-wise. Say it's that high up. And then the girls would take up the rest of the space. Now this is only 2 different variables. You could include more in there. Well, at least the blue and the purple, there's only 2 different parts, categories of that variable. You could have more. And I could have done cat, girl, and boy on the bottom and had 3 different colors inside the bars. Next, your dot plot. Notice there's also a dot plot over here with your line plot. For the dot plot, it's basically like a bar chart for categorical data. You only have one variable, so nix the gender for right now, and you're just putting X's going up. How many are there? And each X represents maybe 10, maybe 1, depends on the situation and what the problem's stating. But that's a dot plot. Notice if you just put bars around it, you now have your bar chart. The dot plot for, or otherwise known as a line plot. My oldest is in 3rd grade right now, and he came home with a homework assignment and it called it a line plot. Instead of categories down there, you may or may not see a frequency on a y-axis, but they're just basically numbers. So from 0 to 1 to 2 to 3, the x's could be in between the numbers or on the numbers, depending on if you have discrete or continuous variables. Usually they'll work with discrete when they do a dot plot like this, and it'll just put little bars going up, or x's, dots, whatever you want to call them, as far as what's what. But again, we're dealing with quantitative variables here, so these are measurements of some sort or scores down here. The time plot. The time plot will always have time on our x-axis. Maybe it's years, weeks, months, days, and then a frequency going on over here. Maybe these are car crashes for a certain age group, certain gender, who knows. It's the only plot that will have dots on the graph and actually connect the dots with a line. So I believe you see these more in AP Human Geography with demographs. Maybe there's a constant here and then it goes back up. When you're talking about a time plot, you're going to want to be able to discuss any peaks, changes in the trend or pattern, like any time that the graph suddenly goes up or when it suddenly goes down. And then also talk about the overall trend. Make sure that everything is in context. And I didn't do the description part down here with our dot plot, so for the dot plot here, We would need to talk about SOCs, of course, your shape, outliers, center, and spread. But because of how this is grouped, for example, if it suddenly had like a 6 here and then a 7 and there's another dot spot right here, you're also able to talk about gaps, clusters, and also whether or not it's unimodal or bimodal. Kind of goes along with the whole cluster thought process, but definitely mentioning if there's clusters in there and how many peaks basically there are. Think of modal is just like your mode, how many modes you have. Okay, going up to your stem plot, we have basically your plot where, depending on your label that you have or your key, you might have your tens in the middle are on your left hand side, and then the numbers in the ones digit on the right. Remember, they go in ascending order as you go up. And we haven't gotten to histogram yet, but the nice thing with your stem plot is if you turn it to the side and you put bars around it, it becomes that histogram. We could also have well, I mentioned a key. Let me slow down. We could say 3/1 equals 31. It could also be 3.1, 3100, depending on what the key says and what the problem's about. You could also have your back-to-back stem and leaf plot where there's numbers in the middle, and then there's numbers going out, maybe a 0, a couple zeros, and a 1, 2, 3, 7, and then just a 9, and over here maybe we have a couple 9s, and then a 1, and then some 4s, and a 5. So you can compare the two distributions. There's also your split stem, where if maybe there's a real long grouping here, rather than counting by tens, I could count by fives. And it would make more sense if they would just repeat the number on the left-hand side, but a lot of times they don't. And they'll just put a dot right there, and then a 1, and a dot. So for the 0, I'm only going to go up to 4, and everything 5 through 9 would be in this second row right here. So maybe 1 and a 4, and then I could have a 5 and an 8 and a 9. And then this one down here would be like a 10, 11, and then if I wanted 16 and 17, they'd be down there. So you're basically counting by fives. It's just a really strange way to look at it. I doubt you would be expected to make one, probably just asked to describe what's going on in one. So this was called split stem. This one here was back-to-back stem. Remember, the key thing on a stem and leaf plot is it's the only one that preserves your values. So gives actual data, your actual data values. You can actually see the numbers in it. And as far as describing it, you would describe it pretty much just like you would a dot plot down below. I've just run out of room. Box plot. That is, of course, with your 5-number summary. And you would need to label your 5-number summary. If you're comparing two, make sure that they're on the same scale so things line up. Maybe we're going from 0 to 10, and I have one that is over here, and then I have another that's right here. So I can line things up and actually compare where things fall, like 75% of the green one is below the higher is 75% of the blue one. You definitely need to mention shape, center, and spread in your outliers. Remember, there's the outlier test. And if you are asked to compare two distributions, make sure you use those comparison words: greater than, less than, same as, all those great words. Now our histogram actually is the one where you connect the bars. So maybe, and your frequency is on your y-axis. So maybe I have from 0 to 1. So this actually goes up from 0 to 0.9999. 1 is in the next column. This goes from 1 to 1.999. 2 would be in the next column over. And then just like I was mentioning down with the dot plot, you could have a gap, a peak, bimodal. So things to describe your histogram with, definitely you're going to want to talk about socks. You're going to want to talk about gaps, clusters, whether or not it's unimodal, bimodal. These are the things that you cannot tell from a box plot. Okay, so that's pretty much all your graphs. Very thorough, lots going on there. If you flip the page, we've got our frequency. Anytime it's just the word frequency, we're talking about the counts. When the word relative gets thrown in, now we're talking about the percent or the proportion, if you move your decimal over. So, or proportion. Your two-way table organizes the counts of categorical variables measured for the same set of individuals. Two-way tables are often used to summarize large amounts of information by grouping outcomes into categories. So here we have our conditional distribution and our marginal distribution with their definitions, and there's also association and Simpson's paradox. The easiest way to describe this one is to give an example of a two-way table. So let's say first group today, 8A, they were talking about having French fries or onions. Maybe fried onions, not really sure which. And then I think that was Danny, and then Adam wanted burgers. How many burgers? So that we'll say that this is cheeseburger. This is hamburger, and then somebody mentioned mac and cheese. So maybe overall these are sides in your order, and these are your entrees, meal, main part. And then so if somebody had French fries with a cheeseburger, maybe there was 8, maybe 5 had onion rings instead. For those that had hamburgers, maybe there were 3 and 4. The mac and cheese, maybe we had 5 and 6. We can figure out our whole count, our totals going down for those that had cheeseburgers compared to hamburgers and compared to those that had mac and cheese. We can add going across and get the total that ordered French fries. Add going across and we get the total that had onions, or onion rings, I'm going to say. Sounds better. That's 15. So altogether, table total is 31. You only add the row going across on the bottom or the column going down. Don't double it. So, conditional distribution, if we wanted conditional distribution of the sides. This is kind of the annoying part. I could look at French fries, That's my category for my French fries. But then I would have cheeseburger. I'll call that one CB. Is that 8 out of 16. So it's that cell over the row total. So that's 8 out of 16. And then I also have hamburger, call it HB, and mac and cheese. Hamburger is 3 out of 16. Mac and cheese is 5 out of 16. And then those for onion rings. Cheeseburger, hamburger, mac and cheese. We have 5 out of 15, 4 out of 15, and 6 out of 15. That would be your conditional distribution of the sides, and you could compare them. Those that order hamburger tend to order more onion rings, as to those that order a cheeseburger, they tend to order more French fries, and you could actually try to establish an association. Could establish possible association. Of course, we've learned more recently we would need to do a chi-squared test for independence to establish an association between the two. But then there's also marginal distribution. This is the easier one. So there's less to do. Let's say we wanted marginal distribution of sides. Then I'm only going to have either my French fries or my onion rings. So my French fries, I'm going to look back up at my table here, there's 16 out of 31, and my onion rings were 15 out of 31. So 16 out of 31 and 15 out of 31. Without even calculating the proportions or the percentages, we could see those are close to being the same. Simpson's paradox is when people will use the marginal distribution to imply an association, which is not appropriate. It's incorrect. Because here, we could imply that it doesn't matter, French fries and onion rings are ordered the same. It doesn't matter what you order for your meal, you'll have an equal distribution of French fries and onion rings. However, when you look inside with the conditional distribution, you see that things are slightly different. Like you could say there is an association or a relationship between those ordering cheeseburger and French fries. More people that order cheeseburgers tend to order French fries because of how our data is set up. So that's Simpson's paradox, using marginal distribution to wrongly claim association. All right. Next part down here is going back to our quantitative. And that's with the shape, center, and spread. I'm going to kind of include it all together. And I can't hit pause, but people are walking in the door. So, with shape, with shape, if it's skewed to the right, then we know that the mean will be greater than the median. If it's skewed to the left, then we know that our mean will be less than the median. So for the group that just walked in right now, they're probably going to be quiet because I don't want to be on video. you could start Math Excel or work on the multiple choice problems from the packet that I gave you earlier today.
Okay, Ms. Wojcik.
And I'll go over the answers with you after I'm done recording. We could also have a symmetric distribution where your mean is approximately equal to the median. So that pretty much talks about your center. If your data is skewed, obviously these two are skewed, and this one's symmetric. For centers, you should use your mean if your data is skewed, or median, excuse me. And then for symmetric data, we should use our mean. As far as the spread goes, we could use if it's skewed distribution, you can use your IQR. And if it's symmetric distribution, you can use your standard deviation. You could use, what else? Standard deviation, range. Can't think of anything else. Mainly standard deviation and mean are the important ones. Then on here there's their interquartile range. It's just your Q3 minus Q1. Outliers, 5-number summary. Make sure that you're able to show the outlier test. And you remember what it is. It is not on your formula packet. Ben, please be quiet. Scott, whoever's talking. Variance. That's your standard deviation squared. The only time we really use it is we want to combine 2 or more independent variables. That's when we're saying you can't add standard deviations. You can only add variances. So you had to square them, square root them. Standard deviation measures the average distance each value is from the mean. We went into chapter 2. And here's a description of the difference between frequency, relative frequency, I mentioned that earlier. Changes it to a percentage. Cumulative frequency, this is just your counts. And then cumulative relative frequency changes it to a percentage. So here for cumulative frequency, 2 plus 7 is 9. That's where that's coming from. And 7 plus 13 plus 2 is 22. So it adds as it goes along. So there's 44 people total. And then over in the cumulative relative frequency, you end up with 100%. The graph is the confusing part. A lot of times I like to give you this in a multiple choice problem and ask you if there's any, what your IQR is, or what your Q1 is, or Q3. So IQR is Q3 minus Q1. So you would approximate where your Q1 is and where your Q3 is, and go down to your x-axis. So it's looking like your Q1 is 50, and your Q3 is 60, so your IQR would be 60 minus 50, or 10. On the next page, it's talking about relationships. The one plot that we don't usually talk about is the normal probability plot. If they give you one, you're just trying to see if it looks approximately symmetric. It's a graph of your z-scores on your y-axis and your x variable, your data values, whatever, on your x-axis. You're just trying to see how straight it is. If it's straight, then that means it's approximately normal. It is also the last graph option on your calculator. So on your calculator, I believe you would have to actually put in the z-scores first, but if you go to your calculator, it's this one right here, and of course it wants your data list and which axis you're going to put it on, or x-axis. See what happens if we zoom 9 right now. There it is. Doesn't look that straight, there's a little curvature down here, but that's your normal probability plot. Then underneath, there's calculator resources in your textbook on how to do each of these in your calculator. I looked them up, found the pages for you so you could quickly locate those. Chapter 3, don't forget you could also use the book's website and it'll talk you through the technology. And then we went into describing relationships in Chapter 3, which we've used recently with scatter plots. All the important parts when you're describing a scatter plot, your correlation, everything that they could possibly ask you about as far as multiple choice questions, what correlation is, how it doesn't have any units of measurement, how it's not resistant to outliers because it involves your standard deviation. The formulas that you get on the AP exam, the main 3 that you're going to use are these ones. So B sub 1 is your slope, B sub 0 is your y-intercept. How to explain interpreting your slope and interpreting your y-intercept, because that could be 2 parts. That could be 2 parts of an actual FRQ. Extrapolation doesn't come up very often, but it's basically when you're being asked to use predictions that are, make predictions that are outside your X value range. Influential point, we talked a little bit about way back when. It influences the placement of your regression line. It's usually an outline in your X value direction. Then there's your coefficient of determination, R squared. That could be one that they ask about if they give you computer output. And that is also on that one sheet for the language of statistics. It's on the bottom, I think. And then the residual are your actual y's minus the predicted y's. Residual plot, what it does. Again, we just went through all these. Then you have your standard deviation of your residuals. That S value that's on your computer output, it's your typical prediction error when using your least squares regression line, like how off your equation will be using this y equals your y-intercept plus slope times x. When you're using that, how off your predictions are from the actual on average. Then back here, if your data is nonlinear, things that they may have done, I highly doubt that you'll be asked to linearize data. It takes too much time and there's too many different possible answers that they wouldn't want to grade it. But you could end up seeing it in a computer output situation, so I would definitely look at the 2 pages mentioned here because it shows you what it will look like and how to go about solving with transformed data. Okay, that's all for now. Stop.